and it's going to be relatively easy compared to what we did last week. Okay, think of it this way. Somebody's having a heart attack, right? So what do? They shock the heart usually. They use something called a defibrillator. How does it work? What they do is they shock the heart. They pump like 20 amps of current into the chest cavity, and they pump 20 amps of current into the chest cavity for a fraction of a second. To be precise, it's 2,000th of a second. So what does it do? It stops the heart. When the current gets to the heart, it's going to stop it momentarily. The purpose of stopping the heart is to reset the heart. Heart is an electrical organ. When you stop it, when you shock it, when you stop it, and when you let it go, it resets itself. All right. So if the heart is fibrillating, you have to defibrillate it. Fibrillating heart is a heart attack. So which means that it's going to irregular heartbeat. And then when you put more than an amp of current into the chest cavity, when you put an amp of current into the heart, it's just going to freeze it. It's going to stop it. All right, so the couple of things to focus: 20 amps of current. They pump 20 amps of current into the chest cavity within 2,000th of a second, almost 1,000th of a second. I got news for you. This 20 amps of current is also the same amount of current that gets pumped into the body of a person who's being executed on the electric chair. The electric chair uses the same amount of current, so this amount of current is deadly. So you're pumping 20 amps of current into the chest cavity to save somebody's life. And the difference between the electric chair and saving somebody's life is the duration. It's 2,000th of a second. It's a risky operation. It's a sensitive operation, as you can tell. In essence, you're generating mini lightning. It's a controlled lightning. And you control the amount of charge that you're depositing. On top of that, you're controlling the duration of this charge, to make it safe. So how do they control the duration, and how do they control how much charge that they're going to deposit into the body? They do so by using capacitors. All right, so the capacitors are charge storage devices. They've been around for a long time, almost 100 years, obviously. All right, so here's a heart defibrillator that you end up using. This is the amount of current that gets pumped in. This is the amount of charge per second that gets pumped into the body cavity, chest cavity. And this is the duration. So you control the amount of charge in the form of current, and you also control the duration of it. The camera flashes do the same. All right, so this is done using a super fast flash. Notice that it's able to flash for a duration, and duration is going to be 0.3 microseconds. This is less than a millionth of a second. All right, so the discharge time is highly controlled under these circumstances. So the discharge time here is going to be 0.3 microseconds, 0.3 millionth of a second. So how do you control the amount of charge that you're able to discharge, and how do you control the discharge time? That was Franklin's idea. So he was trying to prove that the lightning is the same as the sparks that he was generating inside a laboratory. And then, so let's get back to the lightning jar.
The jar, trying to catch, and charge is poured down the wire.
All right, guys, this is the earliest version of a capacitor.
Into the water.
So the negative charge is going into the bottom.
If the jar rests on an insulator, a small amount builds up in the water.
So inside is getting negatively charged.
If instead the jar is held by someone as it's being charged, positive electric charge is sucked up through their body from the ground to the outside of the jar.
All right, so the inside is negatively charged. You touch it from outside, and then the fact that the inside is negatively charged means that positive charges will travel through your body to your hand.
Trying to cancel.
So the inside is going to be negatively charged, the outside is going to be positive charged.
The negative charge.
And there won't be any discharge because you have an insulating material in between.
Inside.
The setup is known as a capacitor. So now this became a charge storage device. All right, so one region is negatively charged. That's the inside region. The other region is positively charged. That's the outside region. And there's no chance of discharge because the charges cannot go across this region. And because there's an insulating material in between. In this case, it's glass.
Positive and negative charges are stopped from cancelling out by the glass, which acts as an insulator. So instead, the charge just grows and grows on both sides of the glass. Then,
all right, now if you touch the top, you'll complete the circuit, which means that you're going to allow these charges a pathway to become neutralized, to become discharged. So which means that the positive charges will flow through your body and negative charges will flow in the opposite direction. You end up creating a mini lightning
the top of the jar with the other hand
within that region and through your body.
Completes the circuit, allowing the negative charge on the inside to pass through the hand to the positive on the outside.
Initially, you will see a spark.
Finally, cancelling it out. The movement of this charge causes a massive shock and often a spark.
All right, so there's going to be a shock and there's going to be a spark. So the question is why? The only thing that they were able to determine, the electric fish, when it shocks you, the amount of charge going through your body is going to be much higher. It gives you a lot more charge at extremely low voltage. So the voltage is going to be extremely low. All right, so what's the meaning of it? Small voltage, big charge. What's the interpretation of that? So that's something that we will do next week. When you're looking at a lightning jar, however, the voltage is really, really high, except the amount of charge is low. All right, so and yet both of them, one is going to give you a spark, the other one is not going to give you a spark. In both cases, you will feel the shock, in essence. All right, so I said lightning jar is a capacitor. So what's a capacitor? I gave you guys a little bit of a description of it. So capacitor is a charge storage device. You store the charge. The simplistic model of it is a parallel plate capacitor. So you have two parallel plates. One plate is going to be charged up positively. The other plate is going to be charged up negatively. All right, so this is going to charge up positively. The other one is going to charge up negatively. All right, so how do you charge up these plates? Use a battery, in essence. So here's your battery. This is the negative terminal. This section is going to become negatively charged. This is the positive terminal. It's going to charge up the other plate positively. All right, so the capacitors. Here's the electronic symbol of a circuit. Here's your voltage supply, which is known as a battery. So this is your power supply. This is what supplies you with the energy that you need. Positive terminal, the taller bar. Negative terminal is the shorter bar. All right, so the positive terminal is going to positively charge up this end. Negative terminal is going to negatively charge the other end of the capacitor. All right, now it's charged up. So the amount of charge that you deposit depends on the voltage supplied by the battery. All right, so if you want to turn this into an equation, this thing that looks like a Jesus face symbol, it's not. It's known as proportional. So charge is going to be proportional to the voltage. So what you do is, if you want to get rid of a proportionality constant, if you want to get rid of proportionality, you have to multiply the right-hand side with something called a proportionality constant. All right, this is a mathematical description of how you turn these proportionalities into an equation, which I don't like. A lot of reference books, the physics books, the textbooks have this description. Because this term C, that most textbooks refer to as a proportionality constant, actually means something significant. This is known as capacitance. It's the ability to hold a charge. So instead of using proportionality constants, this and that, what I'm going to say is I'm going to say the amount of charge that capacitor can store depends on the voltage. Also, it's going to depend on the capacitance. All right, it's ability to hold a charge. All right, so the amount of charge that you can store in a capacitor depends on the voltage supplied by the battery. Also, it's going to depend on the capacitance, the ability of that device to hold a charge. All right, and then I'm just going to go from textbook definitions to my own. It's a little bit more intuitive. So the capacitance is going to represent the amount of charge that you can store in the device. All right, so the capacitance is going to represent the amount of charge that you can store in a device like a capacitor. All right, so what do we know? Amount of charge that you will be able to store, it depends on the voltage supplied by the battery. And it's also going to depend on the capacitance, the ability to store charge, or the amount of charge that it can store, right? That's it. That's the full description that we got. So last week we talked about voltage. So that's going to be the amount of energy supplied by the battery, which is going to be stored within the capacitor in essence. And now this week we're talking about capacitance. So the bigger the capacitance is, the more charge it's going to be able to hold, which means that bigger the capacitance is, more charge it's going to be able to store. Bigger the voltage is, more charge you're going to be able to put on it. And bigger the capacitance, more charge you're going to be able to put on it. Now, capacitance depends on geometry. So let's talk about capacitance. So here's our battery. All right, so we'll charge it up. This positively, this one is going to be negatively charged. Positive or negative, the net charge is the same. All right. Both plates will have the same value of charge. So amount of charge that you can store depends on this area. All right, so larger the surface area is, more charge you're going to be able to store on it. All right, so that's what it means. So capacitance depends on the area. Bigger the area is, the more charge it's going to be able to hold. Makes sense. Smaller the area is, smaller the amount of charge it's going to be able to hold. Also, capacitance is going to depend on the separation distance between these two plates. Closer they are, more charge you're going to be able to store in it. All right, so the bigger the area, more charge it's going to be able to hold. Closer the distance between two opposite charge regions, more charge it's going to be able to hold. So capacitance is going to go up. All right, so the next thing is the trick that we will get to employ that the physics books like. Physics books usually like. All right, so here's what it is. You got two proportionalities, turn it into an equation by multiplying it by a constant. All right, so the constant we employ here is going to be epsilon naught. Okay, so the question is, why this constant? Why not something else? Well, that's a discussion for another time. All right, so we will have that discussion. Not today, but during the next lecture. All right, so A is the area, D is the separation distance, C is the capacitance. So what is the unit for capacitance? Let's figure that out. So Q is the charge, coulombs, V is voltage, volts, C is going to be Q divided by V. So it's going to be coulombs divided by volts. That should be the proper unit, except we're describing capacitance by using two names, coulomb, Frenchman, volt stands for volta, that guy is Italian, so you take a French and then divide it by an Italian, so what do you get? Well, if you follow logic, you should get someone who's British if you take someone French divided by Italian, evidently. So as a result, we end up getting a different person out of that conversion process. All right, so charging a capacitor, you need to use a battery. Here's your battery symbol. This will become negative charge. This becomes positive charge. L represents low voltage or negative voltage because this becomes negative charge. H represents high voltage or positive voltage because that becomes positive charge. So the amount of charge that the capacitor stores depends on the capacitance and the amount of voltage. All right, capacitance depends on geometry. Larger the surface area is of the plates, more charge it's going to be able to store. Smaller the distance of separation is, the more charge it's going to be able to store. All right. So Coulomb divided by volt is going to give you Faraday. Instead of calling it Faraday, we call it Farad. So Coulomb divided by volts is give you F. F stands for Farad, short for Faraday. And that's the proper unit that we use for that purpose. All right, so more about Faraday later. Physics 1 is about Newton, Physics 2 is about Faraday. One of the biggest names in physics. All right, pick out the best answer. And put it in the chat. All right, so the best answer, Coulomb per volt is going to be Farad. So D is the best answer.
Analytic field.
When a battery is connected between two pieces of metal, it forces charge to flow from one to the other until the potential difference between them is equal to the voltage of the battery. That creates an electric field between them. If the voltage is doubled, so is the charge. So is the potential difference. And so is the electric field. In general, the charge transferred is proportional to the voltage applied, and the constant of proportionality, C, is called the capacitance.
All right, so let's
Analytic field.
one more time.
When a battery is connected between two pieces of metal, it forces charge to flow from one to the other until the potential difference between them is equal to the voltage of the battery. That creates...
All right, so the battery is going to charge up the capacitor. You can only charge up a capacitor to the voltage or potential of the battery. All right, so you're going to keep charging up the parallel plates until the voltage difference between the plates equal to the voltage supplied by the battery. That's what it means. If you're using a 12-volt battery, you're going to be able to charge up the plates until the voltage or potential difference between the plates is going to be 12 volts. All right, so that's what it's talking about. All right, so capacitors can only be charged up to the voltage supplied by the battery. That's it. So the amount of voltage supplied by the battery is going to be exactly the same as the voltage difference between the charged plates. So which means that the charging process is going to take a while, usually. Depending upon the capacitor, it could take a millionth of a second, billionth of a second, or it could take a thousandth of a second, hundredth of a second. So it depends on your capacitor. All right, so this is the voltage supplied by the battery. All right, so which means that this plate is going to get charged up positively. This plate is going to charge up negatively. And the charging process is going to continue until the voltage or potential difference between the plates is exactly the same as the voltage supplied by the battery. Put differently, the amount of energy supplied by the battery is going to be the same as the amount of energy stored inside the capacitor. It's not going to be more, it's not going to be less. This is known as the conservation of energy. So the amount of energy supplied by the battery is going to be the same as the amount of energy stored inside the capacitor. All right, so here's your capacitor. This is going to become positive charge, this is going to be negative charge. This region is high voltage, this region is low voltage. And notice that the electric field points from high voltage towards the low voltage region. So the amount of energy stored within the electric field, within this region, which is separated by the distance R or D, is the amount of voltage amount of voltage difference between the regions. All right, guys, remember the voltage represents the amount of energy stored within the electric field between two opposite charged regions through a distance of d in this case. So this represents the stored energy within this region. So the amount of energy stored within this region depends on the amount of energy which is going to be supplied by the battery. So whatever the battery supplies is the energy, that's whatever the battery supplies is exactly the amount of energy that appears inside the gap of a capacitor. All right, it's a very abstract explanation. So the larger the voltage is, the larger the amount of charge that you're going to put on it. The larger the amount of charge, the stronger the electric field, which means that the more energy is going to be stored in it. And the bigger the capacitance becomes. All right, capacitors look like this in real life. All right, so these are obviously, you can put them into the electrical circuits, and they're charge storage devices. All right, I'm just going to skip this one now. All right, so you got two parallel plates. The amount of charge that you can store on it, so the formulas that we'll get to use. All right, guys, so we'll be doing tons of multiple choice at this point. All right, so charge that you store in a capacitor depends on the capacitance. Capacitance depends on the geometry. And obviously, it's going to depend on the voltage supplied by the battery. And the voltage supplied by the battery is going to be the same amount of voltage in between the plates, in essence. All right, so the voltage represents the amount of energy stored inside the electric field. And the electric field inside a capacitor depends on the amount of charge per plate that you're looking at, per area of the plate that you're looking at. So it depends on the charge density, which is going to be constant. All right, so this represents the amount of energy stored inside the electric field. The electric field is going to be generated by the net charge per plate distributed onto its surface area, so charge density. So this is going to be constant. And the larger the voltage or potential supplied by the battery is, the larger the capacitance is, the more charge you're going to be able to store on it. The larger the charge is, more charge you distribute over this area, stronger the electric field is, the larger the amount of energy stored in the capacitor becomes, also the more charge you're able to store in it. All right, so capacitor acts like a charge storage device per se, but also it's an energy storage device like a battery. All right, so it's more about the batteries starting next week. All right, guys, you will have 30 seconds to answer these questions. So let's get started. You'll have like 10 questions, and then I'll give you 30 seconds for each to think about. All right, so put your responses in the chat. All right, so what do we have? We got two parallel plates, plate capacitors. They're going to be identical in every way, right? Except the size of the plates in the second capacitor is going to be twice as large. All right, so what do we got? You know the capacitance depends on the size of the surface area, right? All right, so if one of them has an area twice as large, it's going to have capacitance twice as large. All right, so if you increase the area, it increases the capacitance. All right, as a result, the capacitance goes up. So the area goes up by 2, the capacitance is going to go up by 2. So increase the area, capacitance goes up by 2. All right, so the best answer is going to be A in this case. So that worked out. All right, so let's figure this out. All right, so what do we have in this case? All right, so we doubled the area, and then we shortened the distance by half between the plates, right? All right, so let's check and see what happens. So if you double the area, capacitance is going to go up. You shorten the distance, the capacitance is going to go up again. All right, so what do we have? Increase the area, capacitance goes up, and then reduce the separation distance, the capacitance is going to go up again. So double the area, capacitance is going to go up by 2. Shorten the distance by half, capacitance is going to go up by 2 again. So capacitance is going to go up by 4 times. So the charge is going to go up by 4 times as well. So the capacitance goes up by 4, charge goes up by 4. All right. So D is the best answer for this one. So those of you guys who got this, give yourselves 5 points. Got this. Give yourself. All right. So increase the distance, the capacitance is going to go down. This was weird. All right. Just you know the answer, but just figure this out. All right. I got distracted a little bit. All right, so let's focus on this one. So what do we have? We got a battery, which is going to be fully charged, and then you remove the battery. All right, so here's what happens when you remove the battery. When you remove the battery, the net charge stored in the device is going to remain constant. So the charge that you placed into the device is going to remain constant. All right, and now what you do is you pull the plates apart, you increase the separation distance between the plates. So the question is, what happens to the potential difference between the plates as they are being pulled apart? All right, there are a couple of ways of looking at it. The first way I'm going to do it is I'm going to just look at the formulas, check to see what happens. The second way of looking at it is something that we will do during the next lecture. It's much more intuitive. All right. So you charge this thing up. All right, so charge is going to be constant. All right, because you are removing the capacitor from the battery. The battery is being removed from the capacitor. So charge is going to remain constant. Now what you're doing is you're increasing the separation distance. When you increase the separation distance, that's going to lower the capacitance. So which means that the capacitance is going to go down. Charge is constant. If the capacitance goes down, the voltage goes up. So that's going to increase the voltage. All right, one more time. Charge is constant. Increase the separation distance. That lowers the capacitance. If the capacitance goes down, the voltage is going to go up. All right, so that's what happens. All right, so what happens to the voltage potential difference between the plates as they're being separated? What happens is going to increase for the reasons that I explained. All right, it's going to go up. All right, so distance goes up, capacitance goes down. Capacitance goes down, the voltage goes up because the charge is constant. All right, so this time what do we have? We got parallel plates. So the constant voltage is being maintained by battery. So the battery is part of the circuit right now. And then the plates are being pulled apart. So the question is, what happens to the amount of charge on the plate when you're separating the plates, when the capacitor is still part of the battery? All right, so here's what the battery does, guys. The battery supplies with constant voltage, so the voltage is going to remain constant. So you're increasing the separation distance between the plates. When you increase the separation distance between the plates, this goes up, the capacitance is going to go down. Voltage is constant, capacitance goes down. As a result, what happens? The charge is going to go down. So the amount of charge that it holds is going to go down. So increase the separation distance. The amount of charge that it's going to be able to hold goes down, and naturally the amount of charge that it holds is going to go down. All right, so that's what it means if you follow the definitions. Increase the separation distance, the capacitance goes down, the capacitance goes down, the amount of charge it holds, it's capable of holding is going to go down. So B is the best answer. Amount of charge on plates must decrease. So that's what happens. All right, so let's work on this one. All right, so it's the exact same situation. The battery is still part of the circuit. And once again, the plates are being pulled apart. So what happens to the strength of the electric field during this process? All right, so let's analyze that one. What happens to the strength of the electric field during this process? All right, so what do we have? The voltage is going to be constant. Voltage is going to be constant. So we will increase the separation distance during this process. All right, so there are a couple of ways of doing it. So the voltage is going to be constant. So if the voltage is constant and you increase the separation distance, so D is going to go up. Capacitance is going to go down. So the amount of charge on each plate is going to be smaller. All right, the amount of charge goes down. So you're reducing the amount of charge. So which means that the strength of the electric field is going to go down in essence. So that's what would happen. All right, so which means that we have to use all the formulas. So the voltage is constant. So increase the separation distance. Okay, there's another way of looking at it. The voltage is constant. Increase the separation distance. That's going to reduce the strength of the electric field. That's the fastest way of doing it. But that's not the only way of doing it. Another way of doing it is the voltage is constant. Increase the separation distance. The capacitance goes down. When the capacitance goes down, the charge is going to go down. When the charge goes down, the strength of the electric field is going to go down. All right, so there are two ways of doing it. Either way, you expect the strength of the electric field to go down. So it's going to decrease. All right, so the strength of the electric field is going to decrease when you increase the separation distance. All right, let's work on this one. All right, so this one is actually straightforward. We kind of did this many times over. So it's disconnected from a battery while you're increasing the separation distance between the plates. Because it's disconnected from a battery, the net charge is going to be constant. So what effect will this produce on the capacitor? So it's going to decrease the capacitance, guys. So increase the separation distance between the plates immediately, the capacitance is going to go down. Because you're changing the geometry, it's going to decrease the capacitance. All right, let's work on this one. All right, I'm gonna give you 10 points for this one if you can get it right. All right, so this one is the one that most students usually miss because this is a bit of a conceptual question. I kind of gave the answer in the previous question, and obviously you got the answer for that particular question, but you didn't really generalize it. Capacitance only depends on the geometry. All right, so which means that the capacitance is not going to change. Capacitance only depends on the geometry. So you can vary the strength of the electric field up or down. It makes no difference. So make the electric field weaker, the voltage is going to go down. The voltage goes down, the amount of charge it holds is going to go down. That's it. It does not affect the capacitance because the capacitance only depends on the geometry. Just remember that capacitance, the ability to hold a charge, depends on the geometry, nothing else. No external factors. All right, so most people usually miss this. All right, so
The electric field in a parallel plate capacitor is really due to sheets of opposite charge facing each other on the metal surfaces. The field between the sheets is constant. The two sheets of opposite charge attract each other and hold each other in place. That's why a capacitor is such a useful device. If the voltage is held constant by a battery, the charge, and therefore the capacitance, changes inversely as the distance between the plates, and is proportional to the area of the plates.
all right, so the capacitance only depends on the geometry and nothing else. All right, all right, a couple of problems that I asked you guys to focus on. So this is one of those problems. All right, so you got a parallel plate capacitor. There's going to be a voltage difference between these two plates. Low voltage is the negatively charged region. The high voltage is the positively charged region. This negative charge, because it's placed right next to a negatively charged region, it's got tremendous amount of potential energy. It's got low voltage, low potential, and high potential energy. All right, voltage is going to be low if the region is negatively charged, so it's going to give you a negative voltage or potential. If the region is positively charged, it's known as high voltage. High and low, just think of it in terms of altitude. All right, so high voltage represents a higher elevation, the low voltage represents a lower elevation from the perspective of a positive charge. Okay, so that's how we look at things, and that's the way we were looking at things last week. Okay, so once again, let me just go over the terminology. Low voltage represents a negatively charged region. The high voltage represents a positively charged region. All right, so this negative charge is at the low voltage or potential, but it's at high potential energy. All right, so potential energy is the amount of energy stored in it. All right, so within this region, you have the electric field. The electric field is a conservative force field. So the electric field acting on negative charge is going to induce a force on it in the opposite direction of the electric field, thereby accelerating the charge in the opposite direction of the electric field. So what that means is the conservative force acting on the charge is going to convert this potential energy into kinetic energy. All right, so this charge now has kinetic energy. Where did this charge get its kinetic energy from? It got its kinetic energy from the voltage or potential difference, which represent the amount of energy which was stored in the electric field. The electric field acting on the charge energized the charge. Now this charge has potential energy, and then converted the potential energy of this charge into the kinetic energy of this charge as it was going through the hole in the middle of the second plate. All right, so instead of just going blah, 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 blah for 5 minutes, just like that, explaining everything in full and complete detail, we'll come up with an expression, mathematical expression, that's going to tell us about the amount of energy stored inside a capacitor. This just so happens there are two formulas that will do that for us. All right, so we know that the capacitors can store charge as well as energy. We know that because when you take these two opposite leads, and these are wire leads, bring them closer to each other, what's going to happen? There's going to be a discharge. So you end up generating this mini lightning in essence. All right, so positive and negative charges will flow in opposite directions, and they will become neutralized, so which is known as a discharge process. So you end up getting light, and you end up getting sound, and you end up getting heat out of it. That's mini lightning. All right, so the amount of energy stored is going to get converted to heat, light, as well as the sound. So is there any way we can compute the amount of energy stored inside a capacitor? The answer to that question is yes. All right, so instead of doing a derivation for you guys at this level, it's completely unnecessary. What I'm going to do is I'm going to point out the equation. All right, so this equation, capital U, represents the amount of energy stored inside a capacitor. All right, so notice that this equation is going to have two parts. You can either use the first equation to represent the amount of energy stored inside a capacitor, or you can use the second one. All right, let's focus on these two equations briefly. All right, so both equations are divided by 2. All right, that's fine. You have the capacitance here on the equation on the left, you have the capacitance in the denominator on the equation on the right. Okay, so what's the difference between these two equations? This equation is going to express the amount of energy stored inside a capacitor in terms of the voltage, and this one is going to express it in terms of the amount of charge stored in the battery inside the capacitor. Okay, so this is the voltage expression of the amount of energy stored. This is the charge expression of the amount of energy stored inside the capacitor. All right, so those are the two equations that we will get to. All right, so focusing on those two equations, let's answer a few questions. We got 3 minutes to go, so we should be able to finish this up. All right, so we will double the capacitance of a capacitor, holding the charge constant. All right, so what happens to the amount of energy stored inside the capacitor? Okay, so I'm just going to show you how to use these formulas. Okay, number one, holding the charge constant, which means that this is the formula that we have to use. All right, so if you hold the charge constant, if you increase the capacitance, the amount of energy stored is going to diminish. So it's going to store less energy. So hold the charge constant, increase the capacitance, the amount of energy stored is going to diminish. How do you increase the capacitance? You have to bring the plates together. All right, so increase the capacitance, constant charge, increase capacitance, the amount of energy stored is going to diminish, so it goes down. All right, so it's going to decrease to 1/2. All right, so we got that. Those of you guys who got that, give yourselves 5 points, obviously. All right. All right, I'm just going to upload. I'm not interested. That thing is kind of misplaced. All right, so this time we will double the voltage across a given capacitor. So what happens to the amount of energy stored in that capacitor? All right, so this time we have to use the voltage expression. Increase the voltage by 2. All right, the energy is going to go up. If you increase the voltage by 2, you have to also square 2. So which means that the energy is going to go up by 4. All right, so the energy is going to go up by 4. So that's what we end up getting. So we will have to quadruple. All right, guys, so that charge is going to be constant. Increase the separation distance between the plates, the capacitance is going to go down. And then what happens? Let's take a look. All right, so charge is going to be constant. Increase the separation distance between the plates, so that's going to make the capacitance lower. If the capacitance goes down, the amount of energy stored is supposed to go up. All right, so B has to be the right answer for that one. So we talked about capacitors. So what's a capacitor? A capacitor is a charge storage device. The first thing you have to do is charge it up. All right, so here's your parallel plate capacitor. In order to charge it up, you have to hook it up to your battery. So this is your battery, electronic symbol of a battery. All right, so you notice that you got 2 lines. Taller line is going to denote the positive terminal, shorter the negative terminal. Positive terminal is going to charge up one plate positively. Negative terminal is going to charge up the negative plate negatively. So amount of charge that you're going to be able to place on these plates will depend on the amount of voltage which is going to be supplied by the battery. Guys, the battery is an energy storage device. Something we will discuss next week. All right, so it stores the energy within it, and the capacitor is a charge storage device. So you've got an energy storage device hooked down to a charge storage device. So this energy is going to charge up the capacitor. So larger the voltage supplied by the battery, the more charge you're going to be able to store inside the capacitor. That's what it means. All right, so it's a proportionality constant. In order to turn this into an equation, you have to come up with this is a proportionality. In order to turn it into an equation, you have to multiply with the proportionality constant. It just so happens this proportionality constant is known as capacitance. Capacitance tells you about the ability to store charge in this device. So instead of saying this is a proportionality constant, I'm just going to say, hey, I'm just going to call it the capacitance. The amount of charge that you can store is going to depend on capacitance. It depends on the ability of this device to store charge, the ability of a capacitor to store charge. And then what I'm going to do is I'm going to put aside the book definition and then come up with a little bit more commonsensical definition for capacitance. It's going to represent the amount of charge that the device can hold or store. All right, so it's going to represent the amount of charge that it can hold or store. All right, so larger the amount of charge that it can hold, more charge you're going to be able to store in it. Larger the voltage supplied by the battery, the more charge you're going to be able to store in it. So putting these two facts together, you come up with the standard capacitance equation. All right, so capacitance is going to depend on the geometry, meaning that the amount of charge that it's going to be able to hold is going to depend on the geometry. The typical design of a capacitor is a parallel plate capacitor. So you got 2 parallel plates, both of them are metal. One is getting positive charge, the other one is getting negative charge. That's the net charge. So the larger the surface area is, which is gonna hold the charge, the more charge you're gonna be able to store in it. Okay, so larger the storage area means the more charge is gonna be able to hold. All right, so that's one statement. So capacitance depends on the size of the surface area of the capacitor, the plate of a capacitor. All right, so larger the area is, more charge is gonna be able to store. Smaller area is, less charge is gonna be able to store. The next factor is the separation distance. All right, so closer these opposite charge regions are, the more charge you're going to be able to store inside a capacitor. All right, so which means that the capacitance is going to go up. So capacitance is related to the area. It's going to be inversely proportional to the separation distance. All right, so the next question is this epsilon naught. Okay, where do we get that from? From a mathematical perspective, okay, once again, you got your proportionality. So C is going to be proportional to A. Capacitance is going to be proportional to area. Capacitance is going to be inversely proportional to the separation distance between the plates. And so in order to turn this into an equation, you have to multiply with a constant. So the constant in this case happens to be epsilon naught. So the question is why? All right, so that's not very evident, obviously. So where did we get that from? Everything else was kind of common sense. So you can kind of reason everything except, I mean, among all the symbols that we could have used, constants, like you got speed of light, and why end up using this? Or instead of using K, the electrostatic constant, why do we use epsilon naught? All right, so this is, okay, here's the reason why it was taking time, guys. Because I had to do some of these derivations just before the lecture. So let me just move this. Now that I asked that question, let me just answer the question. All right, so the question is, where do we get this symbol from, this constant from? Okay, so that requires a bit of an explanation. Obviously, you don't just go, okay, so I'm going to turn this into an equation, and then I'm just going to put a random proportionality constant there. That's not how things work. So which means that this formula that you're looking at came from somewhere. I just arrived at this formula minus this constant by using a little bit of common sense in essence. So you can actually come up with quite a bit of physics on your own if you have a good understanding of what's going on. All right. Obviously, the constants and everything else has to be derived in a sense. All right, so you get a parallel plate capacitor. So we get a parallel plate capacitor. All right, so this is the equation. All right, so the capacitance times the voltage supplied is going to give you the amount of charge that you're going to be able to place on it. So solve before C. Let's come up with an expression for capacitance. Okay, very good. So the capacitance is going to be net charge divided by voltage. All right, so come up with an expression for voltage. So voltage is that you're looking at, that's the voltage difference or potential difference between two parallel capacitors, two parallel plates of a capacitor. All right, so you're looking at the voltage difference between two opposite charge regions. So this voltage difference depends on the strength of the electric field times the separation distance. All right, so this in essence represents the amount of energy stored within the electric field per charge within this gap that you're looking at. All right, so you do a back substitution. All right, and now we need to come up with an expression for the strength of the electric field inside a capacitor, something that we discussed before. Strength of the electric field inside a capacitor is going to be constant because whatever the charge that you put on the plate is going to get uniformly distributed onto the surface area divided by epsilon naught. We end up getting this from the Gauss's law, believe it or not. We did that like the first week or the second week. All right, so we do a back substitution. Q's will cancel. All right, so this is a denominator of a denominator becomes a numerator. As a result, we end up getting the formula that we almost came up with commonsensically, except this gives you the epsilon naught. All right, so that epsilon naught comes out of a derivation in essence. The rest of it was common sense. All right, so what do we know? The only thing you know is the capacitance is going to depend on the geometry. So you got these parallel plates, and then you have to charge up the plates. How do you charge them up? We come out to a battery. Positive charge is going to positively charge one plate. Negative charge terminal will negatively charge the other plate. You got H, you got L. H represents high voltage. That represents the positive charge region. L represents low voltage. That represents the negative charge region. All right, so there's going to be a voltage difference between these two regions in essence. All right, once again, the electronic symbol, E represents a battery in this case, positive terminal and negative terminal. And this represents a capacitor. Okay, so capacitor symbol is always going to be this, whether it's a parallel plate capacitor or not. Okay, so the most significant one that we discussed, the simplest one, is the parallel plate capacitor usually. All right, so you get a switch, which is going to allow you to actually charge it up, or you can put the switch out, and then you can discharge it. All right, so this is the capacitor equation. The amount of charge that you can store depends on the capacitance. Also, it's going to depend on the voltage supplied by the battery. So that's what the formula says. So the amount of charge stored, okay, you're always talking about the net charge, positive or negative place, it's going to be the same. All right, it doesn't matter. All right, so the amount of charge that you can store depends on the capacitance, which is the ability to store charge, and it depends on the voltage supplied by the battery. That's it. All right, so capacitance is going to depend on the geometry and geometry only, nothing else. Larger the area is, the more charge you can store on it. Obviously, the closer the separation distance between the plates, the more charge you're going to be able to store inside a capacitor. All right, so the unit of a capacitor is going to be coulombs per volt. All right, so instead of saying coulombs per volt, in honor of Faraday, it's called Farad or F in general, so it means Faraday, and that's it. More about Faraday later. And when we get to magnetism, we will discuss his contributions. It's quite a guy. All right. So here's the generic equation for the amount of charge stored inside a capacitor, right? Capacitance is going to depend on the geometry. Okay, so what else do we have? This voltage represents the amount of, this is going to represent the amount of energy stored within the electric field between the distance of, between the region of two oppositely charged plates, which are separated through a distance of d. Okay, that's a tough expression. All right, so it's just going to represent the amount of energy stored per charge between two opposite charge regions, which are separated for a distance of d. Okay, it came out better. All right, and within that region, the strength of the electric field is going to be constant in essence. All right, so here's the net charge on plate per plate dispersed over its surface area. All right, so which means that the net charge per area, you end up getting a uniform charge distribution. All right, so this sigma represents the charge density divided by epsilon naught. Okay, so what else do we have? All right, so those are the four basic equations that we get to use. All right, so this represents the energy stored inside a capacitor, within a capacitor, right? That's it. All right, so you can either express it if the voltage is given, you use this part of the formula. If the net charge is given, you use that part of the formula. Okay, I just kind of simplified it a little bit too much, but you kind of get the idea. We'll probably get into a little bit of more detail in it, because if it's hooked onto a battery, the voltage is going to remain constant. If you separate it from the battery, the charge is going to be constant. All right, so you kind of make a decision in terms of what's given to you and what the circumstances are. All right, so if it's hooked onto a battery, obviously, depending upon what you're doing with capacitor, the amount of charge that you're going to store on it is going to change. If you remove the battery from it, the charge is going to be constant. And if you start screwing, just change the plate separation between the plates of a capacitor, and you're going to end up varying the amount of energy that you can store in it. All right, so I think we've seen some examples of it. All right, so now we're going to take a look at a problem regarding this. But before we take a look at our problem regarding this, all right, the problem that we will do, a lot of you guys are majoring in biology or something related to health sciences. All right, I mean, some of you guys want to become doctors, pre-meds. We got pharmacy majors. Some of you guys want to become vets. And so I'm just going to put the emphasis on, obviously, something health science related. And the problem that we're about to solve is the problem that I want you guys to focus on while you're studying for the test. All right. Another thing that we will discuss shortly is this one. This represents the amount of energy stored. Instead of using these two formulas, there's another formula that we will get to use in the future, so I need to put the emphasis on this one. This represents energy density, which represents the amount of energy which is going to be stored within the electric field. Remember, I always say the energy is going to be stored within the electric field. All right, so energy density represents the amount of energy stored inside the volume between the oppositely charged regions. I'm talking about the gap. So the volume of that gap, so this represents the amount of energy stored within the electric field inside the volume of the gap between two opposite charged regions. All right, so whatever that is, we'll get to it.
In 1780, an Italian anatomist, Luigi Galvani, made groundbreaking discoveries.
Galvani made lightning measurements. Galvani took frogs' legs and showed that when it lightened, that they twitched. So he showed that the lightning radiates an electric field which produces a voltage on frog legs.
Throw the switch. Wait, I thought I saw a pulsation of the heart. Dr. Bradshaw is beginning to freeze. You brought this man back to life. The heart muscle simply responded to a terrific electrical shock, that's all.
What was once thought to be science fiction turned out to be fact. A heart beats because every second, electrical impulses spread through the heart muscle, triggering and coordinating a movement. These signals send echoes through the body tissue to the skin, where they can be detected by metal sensors and displayed as an electrocardiogram, an electrical readout that allows doctors to constantly monitor the heartbeat.
Electricity, electrical impulses are all over the body.
The electricity in our bodies is created by chemical reactions between cells.
What triggers the heart to squeeze are these signals, these small electrical currents, which travel from the outside to the inside of the cell every time your heart beats.
Dr. Hugh Colvins is an electrophysiologist at Johns Hopkins University. He uses electricity to treat and cure electrical malfunctions of the heart. Today, he He is implanting a device in a patient who suffers from a condition that causes the heart to beat too fast.
It takes a certain amount of time for the heart to squeeze blood out of the heart, and also for blood to get back into the heart. So if you go very, very fast, instead of squeezing in a rhythmic fashion, it will literally be quivering, and no blood will flow in the body. And within seconds, you'll pass out. And in minutes after that, you'll be dead.
In order to restore the heartbeat, the victim needs an electrical shock.
When you just put these on the body, you get what's called a quick look. That this acts as an antenna. You can see what the heart rhythm is, and if it's not what you want it to be, if it's ventricular fibrillation, then you can go ahead and discharge it. The way that's done is by pushing both of these buttons simultaneously will cause these to fire, and that will give a 360 joule shock across the body. And to the degree that the heart's in between, the heart will be depolarized and normal rhythm will be restored.
In the electrophysiology lab, the technology of portable defibrillators is now being implanted in the body. Hawkins threads a small wire lead down into the heart.
That's up in the pulmonary artery.
The wire lead acts like permanent paddles on the heart. If the implantable defibrillator detects a problem, it will automatically give an electrical shock to the heart within 10 or 15 seconds.
When I put one of these in, you really have this comforting sensation that this patient, it's like as if they're in the intensive care unit forever. That if ever they develop a rhythm abnormality, too slow or too fast, it will take care of it. And it's really this tremendous insurance policy.
The most critical part of the procedure is the testing of the device.
Here we go.
The patient is given a shock that puts his heart into overdrive. The heart starts fluttering rather than beating steadily. Ventricular fibrillation, they call it. Sudden cardiac death. It's the only way to test the device.
When we were putting in the defibrillator is when we induced this ventricular fibrillation, this very fast heart rhythm. You saw a lot of very rapid squiggles on the screen, and that was the heart beating very, very chaotically with multiple short circuits swirling around the heart, resulting in the heart beating 400 or 500 beats a minute. So 10 joules is about 500 volts. Yeah, this shows the whole readout and how we induce it with shock. And this is the and it takes, you can see, about 8 seconds for the device to charge after which you get out of the rhythm.
The trick is to customize the implantable defibrillator so it delivers the lowest level of energy that can still get the heart beating back to its normal rhythm.
There's more and more enthusiasm about the benefits of electricity. I know for many, many years there's a lot of debate over was it better to treat patients with sudden cardiac death with medications or with defibrillators. And now the studies are available showing that defibrillators are better than medications, at least the medications we have now.
All right, this thing is nuts. Okay, so the way to test it is they give this person a heart attack, and then they shock their heart. Okay, take a look at the number. So they're putting in 300 joules of energy. So the capacitor, defibrillator, is charged up to 360 joules of energy. I didn't say charge. I say it's charged up in a sense that that's the amount of energy that they put into it first. And then when they discharge it, that's the amount of energy that gets pumped into the heart, in essence. So what's the meaning of it? Notice that they're expressing everything in terms of joules, in terms of that energy. Another thing which is interesting is they place the capacitor defibrillator inside the heart. All right, there are a couple of numbers here that I'm gonna pull out. So that's 360 joules of energy. All right. Okay, so I'm gonna turn this into a problem for the test. Okay, the thing that we will do is going to be the following. All right, this is problem number 5 from the handout. So what we know, we got a capacitor, so that happens to be our defibrillator. Capacitor has a capacitance, so it's going to be 70 microfarad, and it's going to be charged up to 5,000 volts. Okay, it's kind of weird that the term that we use, when you charge something up, obviously you're putting charges in it, so you can express that terminology also in terms of the amount of voltage that you're putting into it, and then you can express this in terms of joules as well. All right, so the power of the pulse is going to be, if it is administered, so we need to figure out the power, determine the power of the pulse. If it is administered for a duration of 2 milliseconds. Okay, so what are we looking for? So we're looking for the energy stored inside the capacitor. And then also we're going to be looking at the power of the pulse if it's administered within 2 milliseconds, 2,000th of a second. All right, it looks complicated, but it's not. All right, so this is problem number 5. Okay, so blah, blah, blah. So it just tells you what happens when you shock the heart. All right, so the energy stored in a capacitor is what we're going to be looking for. So here's the capacitance of the capacitor. It's going to be 70 microfarad. Okay, what else? And it's going to be charged up to 5,000 volts. So which means that you're going to keep charging it up until the voltage across the plates is the same as the voltage supplied by the external battery. That's what it means. All right, so figure out the amount of energy stored. So capital U is what we will get to use. So it's getting in terms of joules. And then what is the amount of power that you will deliver into the heart? In this case, the body cavity, because we're dealing with an external defibrillator. So this is the amount of energy that we will put into the cavity, amount of power within 2 milliseconds. All right. So microfarad needs to be expressed in terms of farad. Micro means 10 to the minus 6. Milliseconds needs to be expressed in terms of seconds. So mil is 10 to the minus 3. So that's 1,000, 2,000 to the second. Okay. All right. So the amount of energy is stored. Obviously, we have to look at the formulas. All right. So the energy of a capacitor, energy stored inside a capacitor, either this formula or that formula. Notice that these are what's available to us, right? Look at the symbols. So it makes sense to use this portion of the formula. All right. So that's the one we get to use. That's it. It's not that complicated. All right. So we got the capacitance. We got the voltage. All right. So plug the numbers in. Oh, don't forget to square that, which I did immediately, but doesn't matter. When I was calculating it, I squared it. So this is what you end up getting. Power is the amount of energy per time. So that's the amount of energy that you transfer within a certain time period. Amount of work that you do per time. Amount of energy transferred per time. So energy per time is going to be the power. All right. So this is the amount of energy that we transfer within 2,000th of a second. And so we'll express the power in terms of watts. Okay, so when we express power in terms of watts, what happens? Nothing, right? Because no one gets the number in terms of watts. We don't really use watts in the United States. So what do we use in the United States? We use horsepower in the United States, and we got a rough idea what horsepower is because our cars have horsepower. Okay. Got a sports car, it's probably going to be around 300 horsepower. Most cars are around 200, 150 to 200. My Ford Tempo, it was 120, but it wasn't driving like all the horses were pulling in the same direction. All right. So the bigger the horsepower is, faster the chemical energy is going to get converted into kinetic energy, energy of motion, which means that bigger the horsepower is, the sooner you get up to 60 miles per hour. Bigger the horsepower is, the faster you go from 0 to 60. Right? So it's going to take less time. So when I express it in terms of horsepower, so watts, the horsepower, 1 horsepower is going to be 746 watts. So you get rid of the like units. So it's going to give us a horsepower, it's going to be about 600 horsepower. Okay, now let's think about what just happened. All right, so this is a regular defibrillator. Somebody's having a heart attack. All right, and this is the amount of horsepower. This is the amount of horsepower that you just, amount of energy, the amount of energy that you put into the chest cavity. This is the amount of power that goes into the chest cavity. In essence, that's what it means. Reality of it is, what's happening is you're putting in a lot of energy into the chest cavity. Obviously, notice that when they were using an internal defibrillator capacitor that they were placing into the heart, those guys were using 360 joules. Okay. Normally, what you need is you need 200 joules of energy to actually stop the heart. Okay. 200 joules of energy is required to stop the heart, and then these people end up putting in almost 900 joules of energy because the heart is deep within the body cavity, and you're hoping that at least 200 joules of energy is going to go to the heart. And when those guys are using 360 joules of energy, just in case, right? They want to make sure they're a little bit, they're not overdoing it, but they just want to make sure that they can stop their heart. So they're playing it safe. So now let's take a look at the amount of power that goes into the heart. Let's take a look at the power that actually stops the heart, the amount of energy that stops the heart in terms of power. So notice that this is going to be 1,000 watts. Expressed in terms of horsepower, it's going to be about 140 horsepower. When somebody's having a heart attack, guys, it's almost like 140 horses just tugging on your heart in order to actually stop it and restart it again. So that's what it takes. All right. So the stuff that we will be interested in next week is what is the amount of current that goes into the heart, because we will express this in terms of the amount of current in the future. So this is the power. So this is the amount of energy that gets deposited into the heart in order to stop it for a fraction of a second. So this is the amount of energy deposited. This is the amount of energy deposited into the chest cavity for a fraction of a second, for 2,000ths of a second. And this is the amount of energy that gets to the heart, ideally, in order to stop it for a fraction of a second. So that's what it means. All right, so this is one of the problems that I want you guys to focus on. So because it's related to biology, obviously, it's related to health science. And so I'll probably give you some similar to that. All right, let's talk about the energy density. The only reason why I'm going to talk about this one is because we will get to use this a little bit. All right, so this formula represents the amount of energy stored inside the capacitor. All right, so it's just a generalized expression. We just used that a couple of minutes ago. All right, obviously it's going to depend on the capacitance. It's going to depend on the voltage difference between the plates that we're looking at. So why not just figure out the amount of energy stored within the volume of a capacitor? So whenever I'm talking about the volume of a capacitor, so I'm looking at the volume between two opposite charge regions. All right, so I'm talking about this green region. Okay, so what do we know? We know that based on the discussions that we had last week, we know that the energy is going to be stored within this electric field, electrostatic force field, between these two opposite charge regions. And this region is a volume, as you all know. All right, so this green region is going to represent the energy density, or the energy stored within the volume of the space, the gap that you're looking at. All right, so that's what it means. So what is the amount of energy stored within the volume of a capacitor, in essence? All right, so take a look at C. C is the capacitance. We know that's related to geometry. All right, so we do a back substitution. All right, so D represents the separation distance within this opposite charge regions of that, within that gap. All right, so this V is going to represent, all right, this one is going to represent the potential difference between those two regions. Potential difference represents the amount of energy stored within the electric field between the distance of these two opposite charge regions that we're looking at. So we have an expression for strength of the electric field within the separation distance between these two opposite charge regions represents the amount of voltage. So we'll do a back substitution again. All right, so E squared times D squared. All right, notice that there's D. So D is the separation distance. All right, so this D is going to cancel that square. All right, so this is our surviving D. So A times D is going to be here. I'm going to leave E squared there. All right, so let's focus on A times D, the meaning of that. Area times the separation distance. All right, so I'm going to go to a three-dimensional representation. You got your parallel plates. A represents the area of each and every plate. It's going to be the same in this case. D represents the separation distance. All right, so the area times the separation distance gives you the volume, right? So area times the separation distance gives you the volume. All right, but don't confuse this volume with that volume. Okay, I make this fancy volume. All right, this represents the volume in this case. So do a back substitution. All right, so my volume term. Okay, so this is the total energy stored inside a capacitor. All right, and so what I'm going to do, total energy divided by the volume is going to give us the energy density. So what I'm going to do, I'm going to divide both sides by volume between these two opposite charge regions. So it's going to give us our energy density. So the energy density represents the amount of energy stored within this gap inside the electric field. That's it. All right.
Really quickly.
Okay, go ahead.
What is the symbol for energy density?
All right, symbol for the energy density is the lowercase u. Okay, I see what's going on. I made it too fancy. All right, so this one is capital U. This is a lowercase u. All right.
Okay, thank you.
Give yourself 5 points. Okay, guys, if you have a question, more than likely someone else has the same question. All right, don't be embarrassed. All right, just ask the question and then I'll try to clarify. Because this and that in my handwriting, they kind of look the same, and this looks kind of weird. At least this V and the other V are not the same. I was able to explain it. All right, so lowercase u represents energy density. Energy per unit volume. The capital U represents. All right, once again, you're not responsible for the derivations, but I'm hoping that you were able to follow it because that represents the amount of energy stored within the volume of a capacitor, and the energy is going to be stored inside the electric field. And at the very least, you can see that you can actually come up with these little equations. I don't know if you can come up with them on your own, but you can at least follow it, right? Okay, so because you guys understand algebra well enough, so that at least you know that we're not getting this stuff from space aliens. Unless, of course, I'm a space alien, so we'll find out. All right, guys, take a break for 10. It's 7:33. Take a break for 10. Resume the recording. Okay, I've done these lectures before, so you will get an edited version of it regardless, but it's a good idea to keep recording everything sometimes. All right, give yourself 10 points for that one. All right. Okay, so I'm trying to come up with a conceptual explanation for it. The only conceptual explanation that we came up with so far is, we keep repeating it, strength of the electric field goes down because of the polarization process. Induced electric field is going to oppose the original electric field. So the summation of the values is going to reduce the overall electric field. Electric field represents the amount of energy stored. The voltage represents the amount of energy stored within the electric field. Obviously, if the electric field value diminishes, the amount of energy stored within the capacitor is going to go down. So we got that. So that's commonsensical. You can kind of explain and justify that page. And when you move on to the next page, there's, okay, so these are known as derivations. I'm just manipulating the symbols around. One of the worst ways you can do physics, but magically, here's what happens. What happens is when you place a dielectric material, the capacitance is going to go up. If the capacitance goes up, obviously, that's the ability to store more charge. It's going to be able to store more charge in it. So the question is, why does the capacitance go up? All right, so what happens that causes the capacitance to go up? So we need to come up with some kind of a conceptual explanation for it that makes sense instead of just manipulating equations all over the place. All right, so let's go in that direction just briefly. All right. All right, so I think you guys got that, right? So strength of the electric field diminishes, so we got that. Cool. You guys got that once. Okay. That's for more advanced physics course, so let's just ignore that one. All right, so what happens to capacitance? And what happens to capacitance is, all right, very good. It's got dielectric increases the capacitance. So now it's going to be up to certain more charge. You just got 5 points for them. All right, so what are we looking at? All right, so battery, this is charged up. There's going to be a voltage difference. You get a voltmeter, it just reads the voltage difference. It measures the voltage difference. All right, so as soon as you put a dielectric, the voltage is going to go down. All right, so that's what it indicates. All right, so you can justify that. This becomes polarized. The strength of the electric field goes down. The electric field is where the energy is stored. As a result, the voltage is going to go down. So the voltage represents the amount of energy stored in the electric field. So that part we got. All right, so what happens to the charge, amount of charge, when you place a dielectric material? Capacitance is going to go up, the charge is going to go up, right? Here's the original charge, so the charge is going to go up. The amount of charge it's going to be able to hold is going to go up. So the question is why? Why would the capacitance go up? That's the case. All right, so, okay, so what are we looking at? So if you put a capacitor, you put a dielectric inside a capacitor, what happens? The voltage is going to go down. We discussed that. All right, the voltage is going to go down. What is it that I'm trying to do here? Okay, whatever. All right, so let's talk about capacitors in circuits. Capacitors in circuits. All right, so we got 3 capacitors, and all 3 are hooked onto a battery, and all these 3 capacitors are in parallel to each other, and they're all connected to each other. All right, so this is the amount of charge on the first capacitor. This is the amount of charge on the second one, amount of charge on the third one. Okay, all of them are connected to the same battery. So the negative terminal of the battery is going to charge left-hand sides of these capacitors negatively. The right-hand sides will be charged up positively. All right, this is the voltage supplied by the battery, and this is the voltage difference between each and every single capacitor, parallel plate of each and every single capacitor. Notice that each and every single capacitor is going to be charged up to the same voltage supplied by the battery. All right, this is known as the conservation of energy. So what happens to the overall capacitance of a circuit when you have 3 capacitors connected in parallel in this fashion? All right, so what is the total capacitance of the circuit? All right, so that's what we're going to be looking at. All right, so what happens to the total capacitance of the circuit? All right, guys. Here's the equation. So this is the net charge. All right, so the amount of charge that you're going to be able to store inside the total capacitor, net capacitor of the circuit. All right, so this is the amount of charge which is going to be stored in the circuit. Let's say that. All right, I think that's a good way of looking at it. Depends on the total capacitance, and also depends on the amount of voltage supplied to the circuit. All right, so the net charge stored in the circuit is going to depend on total capacitance. It's also going to depend on the amount of voltage supplied by the battery. That's what it means, or the total voltage supply in essence. All right, so this represents the total or net charge within the circuit that you're looking at. So the net charge that you're looking at, you're just summing up the net charges. So positive or negative, it doesn't matter. It's going to have the same charge inside the capacitor. So it's known as a conservation of charge. So remember, charge cannot be created or destroyed. So Q net charge here plus the net charge there plus the net charge there is going to give you the total charge, the net charge. All right, so this is the net charge inside the first capacitor. This represents the net charge stored within the second capacitor. This represents the net charge stored within the third capacitor. Okay, so what do we know? The voltage difference within each and every single capacitor is going to be the same as the voltage supplied by the battery. So V1, V2, and V3 will be the same. So we will call that V. And now what we can do is we can just factor V out of the equation. All right, so when we factor it out, here's what happens, guys. Here's your net charge. This is the total voltage supplied by the battery. And this expression that you're looking at, this one is your total capacitance. All right, so the total capacitance of the circuit is simply the summation of all the capacitances of every single capacitor that you're looking at. All right, so what that means is the 2 things you need to know. All right, the conservation of charge, obviously. The second thing is the voltage across each and every single capacitor is going to be the same as the battery. All right, that's the conservation of energy. And the total capacitance is simply you're just summing up all the capacitance values of each and every single capacitor. All right, that's it. All right, so out of that, the conclusion is the most important one. The conclusion is, all right, so just sum up. So these are capacitors in parallel. All right, so the capacitors are going to be in parallel when the potential difference of the battery is going to be the same as the potential of each and every single capacitor. So that's the potential difference across each and every single capacitor is going to be the same as the voltage or potential supplied by the battery. That's what it means. All right, pick out the best answer. Okay, okay, I see that a lot of you guys picked D, which is correct. So there's the same potential difference across both capacitors. That's also correct. If potential difference is the same, depending upon which has a larger capacitance, the one with the larger capacitance is going to have a larger amount of charge. So CA, the capacitor A has a larger capacitance, so which means that there's going to be more charge stored on that one as well. So A and D are the correct answers. Okay, so it's got two correct answers in this case. A and D are correct. Okay, so those of you guys who pick A or D, yours has 5 points. All right, the second way you can connect these capacitors are in series. You got one capacitor here, you got the second one, you got the third one. All of them are connected in series to the battery in this sense. All right, so what's happening here? A couple of things that I want you to notice. This plate, all right, terminal is negative charge, so this becomes negative charge. This terminal is positive charge, so this plate is going to become positive charge. And anything in between that you're looking at is going to become polarized. This is positive charge. This end is positive charge. This end is negative charge. Negative charge is here is going to pull the positive charge to this side. And positive charge is here will pull the negative charge to this side. This is not negatively charged. This negative charge region is going to pull the positive charges here. And obviously positive charge region is going to pull the negative charges here. Everything else in between is going to become polarized. So what that means is each and every single capacitor is going to have the same charge. When the capacitors are connected in series, what's going to happen is each and every single capacitor is going to hold the same charge. That's it. Now, the voltage supplied by the battery, because each and every single capacitor is going to have the same charge, and because capacitance values of each and every single capacitor is different, what happens, the voltage supplied by the battery is going to get split among these 3 capacitors. All right, so the voltage drop across the first capacitor is going to be different from the voltage drop across the second one, and which may be different from the voltage drop across the third one if the capacitance values are not the same. That's what it means. So the question is, when the capacitors are connected in series, what is the total capacitance of the circuit? How do we figure that? All right, so when the capacitors are connected in series, all right, so the potential difference across each and every single capacitor is going to add up to the voltage supplied by the battery. Just remember that. So it's going to add up to the potential voltage supplied by the battery. Okay, so that's going to become our starting point. So the voltage supplied by the battery. All right, so we got the battery here. This end is getting negative charge, this end is getting positive charge, and in between you end up getting polarization. So the bottom line is each and every single capacitor is going to hold the same charge. And if the capacitance values are different, the voltage supplied by the battery is going to get split 3 ways among these 3 capacitors. All right, so they're connected in series. All right, so we will use the capacitor equation. So that's the net charge stored within the circuit. V represents the amount of voltage supplied by the battery in this case. And then C top T represents the total capacitance of the circuit. All right, so what do we know? The net charge is going to be constant. Whatever the charge supplied by the battery is going to be the same on each and every single capacitor, so that's going to be constant. So what's happening is this voltage is going to get split among the capacitors. All right, so first capacitor is going to have this amount of voltage across it. This is the amount of voltage across the second one and the third one. So this is known as the conservation of energy, the amount of voltage supplied. And the amount of voltage stored in each and every single capacitor is going to be the same. So that comes from the conservation of energy principle. All right, so the voltage can be expressed in terms of net charge divided by the total capacitance. So the voltage across the first capacitor is going to be the net charge of the first capacitor divided by the capacitance value. Second voltage across the second one, likewise. The voltage across the third one, likewise. Net charge stored divided by the capacitance value. All right, what do we know? We know that the charges stored in each and every single capacitor is going to be the same as the amount of charge supplied by the battery because of the polarization process. So Q is going to be the same, so I'm just going to factor Q out. And notice that this equation now looks like that equation. So V is the voltage supplied by the battery. Q represents the net charge supplied by the battery. And so total capacitance is going to be given by this term. So if you want the total capacitance, you can only get the total capacitance in terms of a reciprocal total capacitance. So which means that you have to add capacitance values reciprocally in order to get the reciprocal of the total capacitance. That's it. So when capacitors are connected in series, this is how you do it in essence. Okay, so use that formula. Okay, so we're done with that one. All right, pick out the best answer. Okay, you guys give yourselves 5 points. You got it. So it's the same charge, right? Stored on each and every single. Okay, so I don't want to do this numerically, but just give me an idea. If you had to find the total capacitance of the circuit, how would you do it? All right, so that's what we're looking at. All right, so if you want to use the microphone, use the microphone. All right, so if you are looking for the total capacitance of the circuit, how would you do it per se? All right. Okay, so these two are connected in parallel. All right, and this circuit is connected in series with this one. All right, so I would find the total capacitance between these two first. All right, because they're in parallel, what do we do? Sum them up. So it's going to be C1 plus C2. All right, so it's going to give us the total. I'm going to call that C12. It's going to be in series with this one. And then I would just add things reciprocally to get the reciprocal of the net capacitance. So here's what I'm talking about. Sum up these two, so it's going to be C1 plus C2, so it gives you this. And then you add these two up, and then it's going to give you that. All right, so that's. All right, so I'm not going to do it because it's straightforward. Didn't want to waste my time on it. All right, so let's go over some of these questions and finish this up. Okay, so when capacitors are in series, okay, forget it. Focus on question number 4 first. When capacitors are in parallel, explain if the potential difference across each and every single capacitor is in any way different from the voltage supplied by the battery. Okay, guys, the voltage and potential difference across each and every single capacitor is going to be the same as the battery. Okay, so it's going to be the same as the battery. Each and every single capacitor is going to charge up to the same voltage. All right, so it's going to charge up to the same voltage as the battery. When the capacitors are connected in series, all right, so the potential difference across each and every single capacitor is going to be different from the voltage supplied by the battery because the charge is going to be the same. So the voltage across each and every single capacitor is going to depend on the capacitance value of each capacitor. So what happens, the voltage is going to get split among the capacitors. So that comes about because of the conservation of energy principle. Okay, question number 6, explain where and how the energy is stored in a capacitor. All right, so the energy is going to be stored within the electric field between two opposite charge regions. All right, that's it. All right, so when you charge up a capacitor, one region is going to be positive charge, the other region is going to be negatively charged. There's going to be an electric field pointing from positive charge region towards the negative charge region. The electric field is an electrostatic force field, which means that it's got the capacity to apply a force on any charge and cause a displacement. All right, so which means that the energy is going to be stored within the electric field between two opposite charge regions of a capacitor. So what is a dielectric? Dielectric is an insulating material that you place inside the gap. So what does it do? It becomes polarized. Because it becomes polarized, it's going to reduce the strength of the electric field. Induced electric field is going to be opposing the original electric field. So what happens as a result, the strength of the electric field is going to go down. Electric field is what stores the energy. So if the strength of the electric field goes down, the voltage is going to go down. And then for some reason that we didn't really discuss, the capacitance is going to go up. And because the capacitance goes up, what happens is the charge is going to go up. So which means that it's going to be able to store more charge. Capacitance means the ability to store charge. If that goes up, obviously it's going to be able to store more charge. All right, so the question is, why does the capacitance go up? Why does the capacitance go up? Okay, are we done with this? Okay, All right, I was trying to zoom in onto this one. Okay, guys, why would the capacitance go up? Take a look at this formula. Okay, so when you place a dielectric material within this region, what happens to the distance between two opposite charge regions? All right, so what happens to the distance between two opposite charge regions? All right, so what happens to this dielectric material? When you place a dielectric material into this gap, so what's happening is this dielectric material becomes polarized, right? All right, so this end of it is going to become negative. If this is positive charge, this end of it is going to become negatively charged. All right, so if this is positive charge, all right, so this end of it is going to become negatively charged, right? This is positive charge after polarization. So what happens to the distance? Okay, so what happens to this distance between two opposite charge regions? This is your D right now. All right, so this distance is going to diminish. As that distance goes down, what happens to capacitance? The capacitance is going to go up, which means that because we end up reducing the distance between two opposite charge regions, okay, so you got these opposite charge regions, the dielectric material, obviously, when it becomes polarized, this region is negatively charged, this region is positive charge. So the gap reduced, as a result, it's going to be able to store more charges in essence, which means that the capacitance goes up. All right, so that's the reason why. Kind of weird. You don't get that sort of stuff just looking at the equations. You have to kind of, this is something that requires that you visualize it.